Hello, welcome to our Process Simulation Challenge project. Our team includes Benjamin Williams, Cameron Williams, and Catherine Maclean. Enjoy! This is our inspirational quote. My cookie guy only does it if you email him and he has a fantastic snickerdoodle. From Dr. Kipper, allegedly. The overall goal of this project is to build a mathematical model that describes caffeine intake, metabolism, and the development of tolerance from extended usage. Caffeine is a very commonly used psychoactive stimulant and is broken down into three main metabolites in the human body. 85% of caffeine is broken down into paraxanthine, and the remainder is turned into theobromine and theophylline.
Now moving on to our model formulation, we first began by describing the metabolism of caffeine in the body according to first-order kinetics seen in equation 1. Equation 1 can then be solved analytically to produce the equation right below it, wherein the caffeine within the body is described by the initial caffeine concentration within the body times e to the minus rate constant times the time. The rate constant for caffeine in the body is difficult to determine experimentally, and as such, we can use equation 2 that describes the half-life, that relates the half-life of caffeine to the rate constant, and we can sub that equation into our analytical solution to derive equation 3. In addition to modeling caffeine metabolism within the body, we also want to model the metabolites within the body. We can do this seen through equation 5, which specifically describes paraxanthine in the body. The first term represents the metabolism of caffeine into paraxanthine, and the second term represents the metabolism of paraxanthine itself. We can then extend this equation to both theobromine and theophylline to derive equation 6, wherein we see not only the metabolism of caffeine, but also the metabolism of paraxanthine, theobromine, and theophylline. Lastly, we know that the sum of the metabolite fractions for paraxanthine, theobromine, and theophylline need to add up to 1. And the alpha P, alpha B, and alpha L are each individual fraction for paraxanthine, theobromine, and theophylline. Our current model assumes that the person already begins with caffeine in their body and that they consume no more caffeine following this time period. This, however, is not accurate to reality. Instead, people typically consume caffeine over a somewhat short period of time, typically between 30 minutes and an hour, and as such, we need to model this effect of consumption. In order to do this, we can use what's called the Heaviside step function, which is able to turn on a forcing function during a specific period of time. We can see in equation 7 that the caffeine going into the person is equal to m, which is simply just a rate at which caffeine is consumed, times a sum of two Heaviside step functions, wherein the first Heaviside step function has t0, and that is the time at which caffeine consumption begins, and the second time, or a Heaviside step function, has T1, which is the time at which caffeine consumption ends. Adding these two functions together, adding these two Heaviside step functions together, results in allowing us to turn M on and off. And we can see this described in equation 8. However, if we want to model multiple periods over which caffeine is consumed in a periodic manner, we can use equation 9, which extends the sum of Heaviside step functions to contain multiple Heaviside step functions that describe individual times over which caffeine is consumed, and the parameters in this case can be modified, and specifically n can be modified to dictate how many times caffeine is consumed within a certain given interval. Combining all this together and implementing equation 9 into our model, we can then arrive at equation 10, wherein the only thing that changes from the previous slide is our rate of caffeine consumption is negative Kc times the current caffeine concentration plus the consumption of caffeine, which is m times that sum of Heaviside step functions. The last effect we want to model is the development of caffeine tolerance in response to caffeine within the body. There are a couple aspects to modeling tolerance. One is simply that as caffeine accumulates in the body, we expect tolerance to increase. Secondly, is that if caffeine is at a steady amount in the body, which it typically is not, but we can imagine it to be the case, tolerance should asymptotically approach that caffeine level, such that it cancels out all the caffeine. Lastly, caffeine or tolerance itself should begin at time equals 0, should also be 0. We can modify a tolerance with a rate constant that is tau, that is in terms of hours to the -1, and we can see in equation 11 that the rate of change of tolerance is equal to tau times the current caffeine concentration minus the tolerance itself. We can then add this equation 11 to our model, as seen in equation 13, to then have a fifth equation that describes the tolerance over time. Lastly, if we want to accurately account for how tolerance impacts caffeine consumption, typically people will increase their caffeine consumption relative to their tolerance so that they achieve the same effective caffeine amount. What this means is that we need to modify the previous m value we have in our dc/dt equation such that it takes into account tolerance. And we can see this in equation 12, where m naught is simply the initial rate at which caffeine is consumed, and we add to that the tolerance amount in milligrams divided by the same delta t seen in the Heaviside step function. What this allows us to do is achieve the same peak of effective caffeine dose, which is simply the actual caffeine in the system or in the body minus the current tolerance.
So the results from our fourth model, where we keep the actual caffeine concentration at 100 milligrams, we can see that the effective caffeine concentration drops over time. The tolerance increases with each dose and reaches a pseudo-steady state near around 30 milligrams. As the tolerance rises, the effective caffeine peaks decline over time, and between doses, effective caffeine becomes negative, indicating withdrawal-like periods. Also, we modeled caffeine and its metabolites over 14 days. Paraxanthine is the dominant metabolite, peaking at around 20 milligrams, while the other metabolites remain at very low levels. Caffeine is cleared quite quickly between doses due to its half-life. The results from our Model 5, where we kept the effective caffeine concentration constant over a period of 14 days, we saw that the real caffeine had to be titrated up to keep this effective caffeine concentration constant due to the tolerance increasing. In the model, each dose slightly increases to keep the effective caffeine peaks near 100 milligrams, and even with the adjusted dosing, the effective caffeine still drops below 0, indicating withdrawal-like periods. Again, we model caffeine and its metabolites, and we can see that as the dose rises, the metabolite levels rise as well, and the results show that caffeine and paraxanthine drive most of the stimulant effects. From our Model 5, once we increase the time interval to 28 days, we can see some pretty interesting things. First, the model shows tolerance rising at first, then stabilizing instead of increasing indefinitely. Also, caffeine doses level off around 130 milligrams after 4 weeks. This plateau is likely unrealistic, suggesting tolerance modeling needs refinement. Withdrawal effects remain an important feature for future model versions. We also see that when caffeine is taken every 12 hours, the body cannot fully clear the previous dose. This leads to a steady accumulation of caffeine in its metabolites. The minimum caffeine level approaches 40 milligrams, indicating incomplete metabolism between doses. Faster dosing intervals produce significantly higher baseline caffeine levels.
To conclude, we identified an optimal caffeine consumption schedule while noting that tolerance and residual caffeine metabolites will accumulate with prolonged use. This model-based approach could be used to establish and maintain an individualized caffeine dosing schedule that maximizes alertness and productivity. Thank you for watching!